Good morning all. Welcome to the session on system software. In the last class we had a discussion on how we can generate an object code for SIC programming. Since SIC programming, it is supporting only two addressing modes, either direct addressing mode or index addressing mode, then it is easy to calculate an object code for an assembler. So because it is using for all the instructions as direct address. Now I'm taking the same example, just copying the content from one string to another. Just I have written this code by using SIC programming. Just I already taken that program, the same program just I have taken. So here just I want to copy the content from string 1 to string 2. So what the string 1, it is having 3 character string. So it is having the value MCA. Just I want to copy that value from string 1 to string 2. So the same program just I have written. So here just I am using the immediate addressing mode as well. Immediate addressing mode, what these two are representing what index addressing mode with direct, and for these all things just we are using program counter relative addressing mode. So just I already told, so whatever the object code it is going to be generated by an assembler, first it is trying with program counter relative addressing mode with direct. If it is not possible, then it will move to base relative. If it is not possible with base registers, so then it is going to forming that object code in format 4. So here before getting to that one for creating an object code, so first I can use the number of assembly directives to write the program. So here just I can mention the start assembly directive. So just I am giving the starting address as a user, just I can give any value. The program is started at the memory location 1000. So just you can give any value for that. Just I am started that program by using starting location, it is 1000. So here I can also give the name for that program in the label field, whatever the name just you can give, copy string, copying string or moving and whatever. Just I am going to give the program name as copy here. Just I am giving the program name as copy. So once the program is been started, yes of course the program must be ended with an assembler directive end. So it is insisting an assembler, it is directing an assembler, it is end of the program. It is end of the program. So means at the end of the program, after that the control has to be transferred to the first instruction. So for the first instruction just I am giving the name as label name as first only. So for the label name just I am giving first only. So here end, so just I need to mention the assembler directive as first here. So this is a simple program just I have taken. So means assembler what actually is going to do is it is going to generating an object code for each and every instruction. So then it is going to forming a single object file. First we should know how actually it is going to generate an object code for each and every instruction first. As we know that assembler while generating an object code for each and every instruction, first the number of steps will be followed. So what is the first step? It is going to convert the mnemonic value into what its equivalent opcode. So then it is going to convert what symbolic value into its address, and then it is going to convert its data constants like that. So here since it is SIC programming language, so means every generating every object code, so then it is using program counter relative addressing mode. So program counter is always pointing to the first instruction to be executed. Now the program counter value it is 1000. So it is pointing to the first instruction is to be fetched out. What is the first instruction is to be fetched out? That is LDT3. So what is the first instruction? It is LDT3 means. So just for all the instructions we are using format 3. If it is not possible with format 3, so then we will go with format 4. So first we have to write the format 3 instruction format. So in the format 3 instruction format, so here just I am taking like this. So here as we know that the first 6 bits which is used to write the opcode. So the next flag bits which are used to represent what kind of addressing mode for that particular instruction. So here what actually the assembler is going to do is, first it is going to convert the mnemonic field into its equivalent opcode. For every mnemonic value there is 2 digits of hexadecimal opcode is there. So for LDT, first just we have to write what is the opcode for LDT. So the opcode for LDT, it is 74. The opcode for LDT, it is 74. So just I am going to write the 74 like this: 0, 1, 1, that is 7, 0, 1, 0, 0. Just write it first, then we will convert it. Alright. So here 2 hexadecimal digits. After that, since this instruction it is in immediate addressing mode, so means the displacement field should have the value itself. So what is the value? The immediate value is there, it is 3. So means what is the displacement field length? It is of 12 bits. So means we have to represent that 3 in 3 hexadecimal digit. So means 003. So means just we can write 0, 0, 3. Just we have to write like this. So since it is format 3, as of course that what E bit should be 0, for format 4 it is E bit should be 1. So then it is not program counter relative addressing mode. So because it is purely what immediate addressing mode, so it is not related to base relative, hence the corresponding bit should be 0. So the next, it is not related to any kind of index register value, hence that X bit is also 0, but it is immediate addressing mode. So means we have to change the I bit as 1 here. I bit as 1. So means to get the object code for this particular instruction, what we need to do is just we have to combine the 4 digits of this instruction format. So just we have to write its corresponding hexadecimal digit: 7, 5, 0, 0, 0, 3. So this is an object code for the first instruction. What is the object code for that instruction? 7, 5, 0, 0, 0, 3. So means since it is in format 3, the object code length it is 3 bytes. For 6 hexadecimal digit it is 3 bytes. So this is for first instruction. So next, for the second instruction, it is going to generate an object code. So now the program before going to that one, so what actually it has to do is, it has to assign the address for all the instructions. So the starting, what are the assembler directive is having the starting address 1000, is being started with 1000 only. It has to started with 1000. So every instructions are in format 3 only. So hence every time the program counter value must be incremented by 3, because the length of each instruction in format 3 it is 3 bytes. 1000 for the second instruction it is 1003. Now third instruction is 1006. The next instruction 1009. The next instruction 1009 plus 2 it is 12. 12 is nothing but C. Next instruction 100, 12 plus 3 it is 15. 15 is nothing but F. Right. So the next string 1, so it is also in 3 bytes. String 1, how many bytes which are there? 3 bytes. So for the next instruction, just we need to add the number of bytes which are required for this string. So here for this instruction it requires 3 bytes. So means 100F plus 3. So means 15 plus 3 it is 18. 18 is nothing but in hexadecimal digit it is 1 2. So 2 1 1 0 1 2. 1 0 1 2. So what is the length of this string? How many bytes? 3 bytes, because it is having only 3 characters, 3 bytes. So plus 3 it is 10 15. For end it is not required. So for the end assembler directives, the program counter is incremented by only 1 byte. The program counter is incremented by only 1 byte. So now the program counter, it is pointing to the next instruction is to be fetched. Program counter value it is 1003. It is fetch this instruction. Once this fetch this instruction, what actually it is going to do is, it is going to pointing to the next instruction is to be fetched, right? So what is the next instruction is needs to be what? Assembled or generate an object code. So again it is what? Immediate addressing mode. again it is an immediate addressing mode. So here what is the opcode for LDX? For opcode of LDX it is 04. So just I am going to write 04 here, write it first, the complete object code, then we can change that addressing mode bit. So here after that what is the immediate value? The displacement itself, it should have the immediate value, that is 0. So just I am going to representing that by using 3 hexadecimal digits. 3 hexadecimal digits. So here after that it is not format, it is format 3, it is not program counter relative addressing mode, it is not base relative addressing mode, it is not related to index register, but the I bit it should be 1. So after that just we have to make a group of 4 bits, right. So here 0, 5, 0, 0, 0, 0. This is an object code for this instruction, 0, 5, 0, 0, 0, 0. So how many bytes? Or 3 bytes. So means it is format 3, 3 bytes of length, the instruction length. So the next instruction, what is the next instruction? It is LDCH string 1 comma x. Just look at that instruction. This instruction is in the form of what? Index addressing mode with direct. So here the program counter is pointing to this instruction, it is fetched out, again the program counter immediately is going to be incremented to the next instruction. So now what is the program counter value? Once this instruction is fetched out, what is the program counter value? It is 1009. So now the program counter value, it is 1009. What is the program counter value? It is 1009. So now after that just we have to find out the displacement value here. What is displacement? The distance between the displacement between. So for this the program counter value it is 1009. The program counter value it is 1009. So here first we have to find out the displacement value for this instruction. So program counter value it is 1009. So here in which position the instruction is there? At the memory location 1006. So here for this instruction what actually it is saying? Load character from the memory location string 1 at the index value, index register value, whatever the value it might be. At that time for the first iteration the index register value it is 0. So means it has to load the first character from that string to an accumulator, right. So to access this memory variable it has to refer this memory location, it has to refer this memory location. What is the memory location? So where actually that instruction is there? At the memory location 1006, where actually it is there? At the memory location 1012. So means the target address, we know that. What is the target address? So here displacement plus the content of the program counter, the displacement plus content of the program counter. So here we don't know the displacement value, we need to find out the displacement value. Target address minus content of the program counter. What is the target address of that string 1? It is 1012. What is the program counter value? It is 1009. So then what will be the displacement value? 2 minus 9, that is 10. If I am subtracting 1009 from 1002, so here is nothing but 2, just I cannot subtract 9 from 2 here, the hexadecimal digit. So just I need to take a borrow, 16 plus 2 18, 18 minus 9 it is 9, 18 minus 9 it is 9, right. So means the borrow value it is 16 here. So 0, 0, 0. So what is the displacement value? It is 009. So means it is 9 bytes, this instruction is 9 bytes far away from this instruction. This instruction is 9 bytes far away from this instruction. So this is called as displacement value. So means now the displacement value we got. So just write it down, that displacement 0, 0, 9, 0, 0, 9. So what is the opcode for STCH? The opcode for, LDCH. What is the opcode for LDCH? It is 50, 0, 101, 0 0, just I am going to writing directly that complete opcode for that instruction. What is that? That is 50. So now just I need to fill, it is format free, hence E bit should be 0. S of course it is program counter relative addressing mode, it is 1, it is not base relative. S, this instruction it is having the operand field, it is having the index registers, means the index register value must be set to be as 1. Since this value it is direct addressing mode with index register, so means since just we have to set the n bit and I bit as 1 year. So just we have to set the n bit and I bit as 1 year. So now just we need to grouping those bits. So then we want to get the object code for that. So what is the object code? We will get 5, the first bit it is 5, next 3, 0 0 1, 1 it is 3, 1 0 1 0 is nothing but 8 plus 2 10, 10 is nothing but A, 0 0 9. So this is an object code for this instruction. So next we have to find out the object code for the next instruction, that is STCH. So just I am going to writing in the similar way, just I am going to write in the similar way. So here the first 6 bits, the next 6 bits are used to represent the type of addressing mode, that next one it is displacement. So once this instruction is fetched out, so the program counter value it is pointing to the next instruction. What is the program counter value now? What is the program counter value? It is 100C. For this also the displacement value will get the same, that is displacement is nothing but for this instruction string 2 it has to be fetched. How far away the string 2 is there? Only 9 bytes. Only 9 bytes, that is the displacement value. So means 100C. So target address we need to find out program counter plus displacement. So means to get the displacement value, target address minus that is program counter value. What is the target address of string 2? 1015. 1015 minus 100C. 100C. So just we have to subtract 100C from 1015. 5 minus C it is not possible because the C value it is 12. So means just we have to take borrow 16 plus 5 it is 21. 21 minus 12 is nothing but 9. So 900. So means that displacement value it is 009 only. So 009. Just I am going to write the same. Right? What is the opcode for STCH? The opcode for STCH is 54. So 0101 0100. So here it is not, it is format 3, hence it is 00. The program counter relative S, it is not base relative, it should be 0. Then it is not, it is index register, it is having the index register, hence the index register bit it is 1. So now n bit and I bit should be changing to 1. So after that just we have to make a group of 4 bits each. So then we have to write its corresponding hexadecimal digit. So for this we will get 5, 5, 7, 5, 7, 8 plus 2 10, 10 is nothing but A, 009 only. So this is an object code for this, for that instruction. So the next thing, for the next instruction just we need to find out an object code. So what is the next instruction? TIXR T, right? TIXR T. So in this case, that for the TIXR T instruction, so only that, so either we can represent by using 3 bytes or 2 bytes. If it is index operation, just we can represent 2 bytes only, but just I have taken 3 bytes here, so also just I can represent 3 bytes also, right? So here TIXR and with respect to T. So what actually it is going to do is, it is going to comparing the index register value. Index register value must be incremented by 1, and with after that we have to compare that index register value with the register value T. What the register value T it is having? An immediate value 3. So means for this instruction directly we can write. So what is the opcode for that instruction TIXR? It is B8. what is the value for that index register, that the number of, the number of the register T, the number of the register T, it is 5. The number of the index, the register T, the general purpose register T, it is 05. Only 2 bytes are enough, because just I have written all the instructions of 3 bytes length, just I can make this as 3 bytes. Otherwise just you can take 2 bytes. So whatever the program counter value, just we have to increment, just it has to be incremented by only 2 bytes. That's it. So here just I can represent the same by using 00B835. So here it is not related to any kind of program counter, because that value, what the comparison is going to be taking place between the accumulator, index register with the what, with the register T. So hence no need to use that program counter relative addressing mode or anything else like that. So next one is, what is the next instruction? This one. So here at the memory location 100F, at the memory location 100F. So at the 100F, just what we can say is, right, so the program counter value for that, again just for the same thing, just I am going to write this code, this format, NIXBPE. So here what is the opcode for JLT? Opcode for JLT, it is 38. So here 0011 1000. So here the program counter value for this, what is the program counter value? What is the program counter value? It is for that instruction, it is 1012. It is pointing to the next instruction. What is the target address? Move CH. Where actually the move CH is there? Move CH, where actually it is there? At the memory location 1006. Here we will get the negative value. Negative value, it should be represented by using 2's complement method. Negative value, it is going to be represented by using 2's complement method. So here just we need to find out the displacement value here. So here just we have to subtract that program counter value from 1006. So but the program counter value, it is larger than that of the target address. So means just I am going to subtracting 1016 from 1012. So here 16 plus 2 18. 18 is nothing but 1 2. 18 is nothing but, it is 1 2. 1 2 is nothing but C, means 12. 12 minus 6, it is 6 only. So next it is 0 0 0. So means this is the negative value we got. Negative value we got. So means we have to get its 2's complement value. As we know that directly we cannot say that 2's complement value of 006 directly. So what we can do is, so for that what we can do is, so means we can what, convert that value. So here 006 just I am taking here. So just I want to get the 2's complement of that one. So because just I want to get the negative value. So first just I am going to writing its corresponding what, 4-bit hexadecimal digit value 0116. So here 0006. So to get the 2's complement value, first we have to get the 1's complement. So just I am going to write 111 111, again 1001. So to get the 2's complement, just we have to add 1 2. We have to add 1 to the least significant bit of that number. So 1 plus 1, it is 2. 2 is nothing but 0 1 0 1. Again the remaining bits are same. Right. So after that just we need to make a group of this. 15 is nothing but F. 8 plus 2 10 is nothing but it is A. FFA is nothing but the value of minus 6. Minus 006 FFA. So means in the displacement field, so just we have to write 1111 1111, again that is 1010. Since it is format 30, program counter has base relative no, index register no. Since it is direct addressing mode, so just we are changing the bit of N and I bit as 1 here. N and I bit as 1. So now get the object code for this, right? So it is 3. Directly just I am going to write it here, right here only. The object code 3, 8 plus 2 to 10, 10 plus 1 it is 11, 11 is nothing but it is B, 3, B, it is 3B, next 0, 0, 1, 0 it is 2, next F, 8 plus 2, 10 it is A, 3B to FFA, it is an object code for that instruction. So after that this is the constant, this is the reserve byte. So for that constant only that assembler directives byte word, it is going to generate an object code, just it is going to convert into a constant value. For this it is not going to generate any what value, but for reserve byte, reserve word and start and end, for these kind of assembler directives it is not going to generate any kind of object code. So means for that byte, so what is that byte? It is having the character string MCA. So means it has to get the ASCII value. For that ASCII value, just we have to write its corresponding hexadecimal digit. So just you can get the same at the page number 475 in your textbook, the ASCII, the hexadecimal digit for the ASCII value of MCA. So here for M it is 4D, M it is 4D, C is for 43, A it is for 41. So this is an object code, that is the hexadecimal digit of MCA, ASCII value of MCA. So 4D, 43, 41. So just I am taking only 3 length character string because it is easy to represent that what object code. So for the reserve byte, for the end it is not going to generate any kind of object code for this. So this is the how actually we can generate an object code for each and every instructions by using SIC XC machine architecture. So once the object code is being generated by an assembler for each and every instruction, so then it has to write the same instructions to the object file. Just it has to make a object file. That object file, it is having different kinds of records. So means just let's see how it can make an object code. How it can make an object code. Once the object code is being generated by an assembler, the next task of that assembler, it has to make an object file. So what is an object file? Object file, it is made up of number of records. So the object file, it is having 3 different kinds of records initially. So if any relocations are needed, some more records will be added. So here since in basically it is having only 3 records. So here what are the records it is having? The header record, text record and end record. So in the header record, so it is having its own length to represent. So here the first column 1, it is going to represent what kind of record it is. The column number 2 to 7 means 2, 3, 4, 5, 6, 7. So means how many digits? 6 hexadecimal digits means 3 bytes. So means 2 to 7, it is going to using to mention the program name of that program, right? So from the column number 8 to 13, which is used to represent the starting address of that program, where actually it has mentioned in this. If the starting address has not mentioned by using the start assembler directive, by default the assembler will take 000 is an starting address. So the remaining column number, that is column number 14 to 19, so here just we are going to represent the length of the object code of that program. The length of the object code of that program. The length of the object program of that program. So here the next text record, header record, it is having only that informations, the metadata informations of that program name, program length, then object, what is the starting address of that program, these kind of informations will be there. But the content of whatever the actual object code it is there, this object code is present in the text record. is present in the text record. So the text record, it is having its own structure. The text record, the column 1, it is used to represent the type of the text record. Column 2 to 7, column number 2 to 7. So here the object file, it might be having single header record, single end record, and it might be having n number of text records. For the simple program, only one text record is enough. One text record, it is capable of holding 6 hexadecimal characters. 6 hexadecimal characters means 30 bytes, right? So if 30 bytes are filled for the first record, the next text record will be initialized. So means it might be having n number of text records within that. So in this case 2 to 7, that starting address of that object code on that, in that particular text record, starting address of that object code in that record, So column number 8 to 9, it is used to mention the length of the object code in that particular record, the length of object code in that record. So the length of the program, it is different, the length of the record is different in that text file. So how many bytes which are there, so just we need to find out its length. So next, the column number 10 to 16, 10 to 16 means approx 30 bytes, sorry 10 to 69, approx 30 bytes, which is used to having the actual content of the object code, means approx 30 bytes. So the end record, column text record, it is having the column number 1, the type of the record it is column number 2 to 7, the starting address of the object code in that particular record, column number 8 to 9, length of the object code in that record, object code in that record. So the column number 10 to 69, it is having an object code. So the end record, it is having only that column number 1, which is used to represent the type of the record. So then column number 2 to 7, it is used to represent the starting address of that program, because once the assembler encounters the end record, again for loading purpose, it has to pointing to the first instruction of that program. So hence we need to mention the address of that first instruction. So this is the what the minimal requirements of an object file. That object file, it might be having, it should be have only one header record and one end record. It might be having n number of text records. It is depending on the length of that program, So let's see how we can write an object code, object file, how we can create an object file for this program. So here, what is the first program? The program, so that should be having an header record. The header record, it is having its representation H, which is followed by, just I am using this as a separator, but actually it is not using, but for our what convenience, just we have written like that. So means H separator, just I am using. What is the next column? Column number 2 to 7, it should have, 2 to 7 means 6 characters it should have. So means what is that program name? Just I am giving the program name is copy here. So just write it down, copy. So here it requires 3 bytes, one it is of 1 hexadecimal digits, just we need to use, right? Copy. After that what is that? The next one, it is the starting address. What is the starting address? From 8 to 13, again 6 hexadecimal digits. So what is the starting address? 1000. So just I am going to writing 1000 by using 6 hexadecimal digits like that, alright. So after that, what is the next one? The object code length. How actually I can find out the object code length? It's been started from 1000, it's been ended at the memory location 1016, because end, once it encounters the end, so only that previous program counter value will be incremented by 1. So how I can find out the length? It is 1016 minus 1000. So the length of this program, just I need to subtract the starting address from the ending address. 1016 minus 16, that is the length, it is 16. So 14 to 19, so 19 means approx 6 characters, just 0 0 0 0. What is the length? We are calculating 0 0 1 6. This is the length of that file 0016. So the next is text record will be initialized. The text record, the first text record it is there, it is that starting address of the object code in that particular record from this. So here just you can observe that from here to here how many bytes will get 1, 2, 3, 4, 5, 6, 7. 7 into 6. 7 into 6. How many bytes? 7, 6, 42. So means in this case the text file, the starting address from which address just we are using at the memory location is 1000. So just I need to mention its starting address of that particular file. It is been started from here to here. So means 0010. So the next one is 8 to 9. It is length of that record. It is length of that record. So it's been started from here to, it is been started from here to here. So means to get the length of that one, just I need to consider its next what program counter value. So means 1015 minus 1000. What is the object code length? It is 15. 15 bytes. So what is the object code? It is, sorry, what is the length of that record? 15. What is the length of that record? It is 15. 1015 minus 1000 is nothing but 15. Next is it is having an object code. So actually where actually it has been started? 75. What is the object code for that? First instruction 7004750003 05000 again 53 A009. So next 57 A009. So like that up to 4D 4341. So this is the text file. So the next it is having an end record. That end record it is having the starting address. What is the starting address? It is 1000. So this is completely called as an object file. This is completely called as an object file. That object file it is having 3 different kinds of records, that is header record, text record and end record. So here just I took the simple example. For that example how we can write the how we can get the object code and how we can generate an object file. So here the object file it is having 3 kinds of records. All the records it is having its own representation. By combining all those records then it is going to forming an object file. Along those records some more records are also there. Basically these 3 records are enough for simple programs. So let's discuss what the assembler algorithms, that is pass 1 and pass 2 assembler, one pass assembler in the upcoming sessions. Thank you.